Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. This week in astronomy, Zhúlóng Galaxy, dark energy and NASA's solar probe update. Zhúlóng, a distant spiral galaxy, challenges early universe models. Using the James Webb Space Telescope, JWST, an international team of astronomers has made a groundbreaking discovery. Zhúlóng, a massive grand design spiral galaxy residing at an immense distance from Earth. This finding, detailed in a research paper published on the preprint server AR14 on December 17, marks Zhúlóng as potentially the most distant spiral galaxy identified to date. Grand design spiral galaxies, renowned for their prominent, well-defined arms gracefully swirling outwards from a distinct core, are believed to owe their structure to denser regions within their disks. These denser regions act as triggers for star formation, compressing incoming material as it passes through. The emergence of spiral galaxies in the early universe remains a subject of ongoing investigation, with these galaxies being relatively rare at high redshifts. Prior to this discovery, only a handful of individual spirals had been detected at a redshift exceeding 3.0. A team of astronomers, led by Mengyuan Xiao of the University of Geneva in Switzerland, serendipitously stumbled upon Zhúlóng while analyzing data from the JWST panoramic survey. The galaxy, named after Zhúlóng, a mythical giant red solar dragon and god in Chinese mythology, was identified at a photometric redshift of approximately 5.2. This redshift indicates that Zhúlóng existed when the universe was only a billion years old. Despite its young age, Zhúlóng boasts a mass comparable to our own Milky Way galaxy, a remarkable feat for a galaxy formed so early in the universe's history. The study revealed that Zhúlóng possesses a classical bulge and a large, face-on stellar disk adorned with spiral arms spanning an impressive 62,000 light-years. Spectral energy distribution (SED) analysis of Zhúlóng indicates a quiescent-like core and a star-forming stellar disk. Interestingly, the core, exhibiting a red hue, possesses the highest stellar mass surface densities observed among quiescent galaxies. This quiescence in the core aligns with the expectations of inside-out galaxy growth and quenching. While the disk of Zhúlóng continues to actively form stars, its overall star formation rate is relatively low, estimated at 66 solar masses per year. The efficiency with which baryons, ordinary matter, are converted into stars in Zhúlóng is approximately 0.3. significantly higher than even the most efficient galaxies observed at later epochs. These findings strongly suggest that Zhúlóng experienced a period of highly efficient star formation and is currently undergoing a transition phase from a star forming to a quiescent state. The discovery of Zhúlóng has profound implications for our understanding of galaxy evolution. It suggests that mature galaxies, like Zhúlóng, emerged much earlier in the universe's history than previously anticipated, within the first billion years after the Big Bang. Is dark energy real? A new perspective on the expanding universe. One of the biggest mysteries in science, dark energy, may not actually exist, according to a team of researchers at the University of Canterbury in Christchurch, New Zealand. Their analysis, published in the journal Monthly Notices of the Royal Astronomical Society Letters, challenges the long-held assumption that the cosmos expands equally in all directions. For the past century, Physicists have relied on the concept of dark energy to explain the observed acceleration of the universe's expansion. However, this contentious theory has always presented significant challenges. Instead of invoking dark energy, the researchers propose a new model called timescape that explains the observed acceleration without requiring a mysterious force. The timescape model acknowledges that gravity slows down time. This means that an ideal clock within a galaxy would tick slower than the same clock in empty space. Consequently, billions more years would have elapsed in vast cosmic voids compared to regions within galaxies. This temporal difference allows for greater expansion of space within voids, creating the illusion of an accelerating expansion rate as these voids become increasingly dominant in the universe. This research provides compelling evidence that the observed acceleration of the universe may not be driven by dark energy but rather by variations in the kinetic energy of expansion within a lumpy universe. The researchers believe that the timescape model can resolve several key questions surrounding the quirks of our expanding cosmos. The standard lambda-cold dark matter (lambda-CDM) model, which incorporates dark energy, relies heavily on measurements of distances to supernova explosions in distant galaxies. These supernovae appear farther away than expected, suggesting an accelerating expansion rate. However, recent observations have increasingly challenged the validity of this model. The Hubble tension, an anomaly observed in the cosmic microwave background (CMB), reveals inconsistencies between the expansion rate of the early universe and its current expansion rate. Furthermore, recent analysis of high-precision data from the Dark Energy Spectroscopic Instrument (DESI) indicates that the lambda-CDM model does not fit the data as well as models where dark energy evolves over time instead of remaining constant. These discrepancies highlight the limitations of the simplified Friedmann's equation, which assumes a uniform expansion of the universe. In reality, the universe exhibits a complex structure with galaxy clusters, filaments, and vast empty voids. The timescape model acknowledges this complexity, proposing that a simple expansion law consistent with Einstein's general relativity does not necessarily obey Friedmann's equation. The researchers believe that the European Space Agency's Euclid satellite, launched in July 2023, has the potential to test and differentiate between the Friedmann equation and the timescape alternative. This endeavor will require a substantial number of high-quality supernovae observations, ideally exceeding 1,000. While a previous test of the timescape model in 2017 showed only a slight improvement over the lambda-CDM model, the current analysis, utilizing a significantly larger dataset of 1,535 supernovae from the Pantheon Plus collaboration, provides strong evidence in favor of the timescape model. This new evidence may also offer a compelling resolution to the Hubble tension and other anomalies related to the expansion of the universe. The researchers emphasized the need for further observations from Euclid and the Nancy Grace Roman Space Telescope to solidify support for the timescape model. The race is now on to utilize this wealth of new data to unravel the true nature of cosmic expansion and potentially overturn the long-standing notion of dark energy. NASA's Solar Probe Update. On New Year's Day, NASA's Parker Solar Probe brought excitement and groundbreaking updates, as it successfully completed another record-breaking encounter with the Sun. This monumental event marked the spacecraft's closest approach yet, delivering invaluable data and reaffirming its robust performance in the extreme conditions near our star. On January 1st, Mission Control at Johns Hopkins University's Applied Physics Laboratory, JUPL, in Maryland began receiving telemetry data from the probe. These initial transmissions confirmed that Parker's systems and scientific instruments were functioning perfectly following its historic flyby. The telemetry, essentially the spacecraft's housekeeping data, provided critical insights into the probe's health. According to NASA's update shared on January 2nd, the Parker Solar Probe was operating as intended. The systems and instruments aboard the spacecraft had successfully executed the programmed commands, gathering unprecedented scientific data as it ventured closer to the Sun than any human-made object in history, just 3.8 million miles, 6.1 million kilometers, from its surface. This marked another milestone in humanity's ongoing quest to understand our star and its mysteries. The spacecraft, designed to endure the intense heat and radiation of the Sun's outer atmosphere, performed exactly as planned. During this daring maneuver, Parker Solar Probe's instruments captured critical observations of the solar corona, the Sun's outermost layer, and the space environment surrounding it. The successful operation of its systems during this flyby demonstrated the remarkable engineering and planning behind the mission. NASA emphasized that Parker is paving the way for discoveries that were previously beyond our reach, opening a new chapter in solar science. Receiving the telemetry data required a highly coordinated effort using NASA's Deep Space Network, a global system of antennas that facilitates communication with spacecraft across the solar system. The initial telemetry transmission confirmed that the spacecraft not only survived the intense conditions but also adhered flawlessly to its mission commands. This means it collected a wealth of data during its close approach, which promises to provide new insights into solar wind, magnetic fields, and the mechanisms that power the Sun's activity. As the telemetry continued to arrive, the next step for mission control was to prepare for the spacecraft to transmit its full science dataset. This transmission, expected later in the month, requires the probe's most powerful onboard antenna to achieve optimal alignment with Earth. Once received, the data will be analyzed to uncover new details about the Sun's corona, its energetic particles, and its influence on the solar system. The Parker Solar Probe's accomplishments represent a leap forward in heliophysics. Scientists anticipate that the data collected during this historic flyby will answer fundamental questions about the Sun's behavior, including why its outer atmosphere is hotter than its surface and what drives the solar wind that affects space weather around Earth. These findings are critical not only for advancing scientific knowledge but also for safeguarding technologies and astronauts from solar radiation. The mission reflects the culmination of decades of vision and innovation. By venturing closer to the Sun than ever before, Parker Solar Probe is breaking barriers and expanding humanity's reach into the universe. Its success reaffirms our ability to design spacecraft capable of withstanding conditions once thought insurmountable, all while delivering discoveries that bring us closer to understanding the heart of our solar system.